Yes, you can start now.
A very good morning to everyone present here. It's my pleasure to welcome you all to the 9th day of this international virtual workshop on global seismology and tectonics 2021. We'd like to extend a special welcome to our first speaker of today's session, Professor Sima Ghosh from National Institute of Technology, Agartala, India. Madam will deliver her talk on recent seismicity and probability assessment of earthquake occurrence in Northeast and Himalayan region. So before we proceed, may I request our session chairman, Professor J.R. Kyle sir, for his initial remark. So over to you.
Thank you so much. Hearty warm welcome to Professor Sima Ghosh, NIT Agartala, to this global platform for our presentation. And thank you so much for kindly accepting our humble request to participate in this international workshop. Well, I know Professor Sima Ghosh since more than last 1 decade. She invited me to NIT Agartala as adjunct professor and since then I know her. Sorry about the interruption. Since then I know her as one of the bright researcher, very kind, warm, and dynamic personality with positive thinking. She is now heading the civil engineering department in NIT Agartala. And we really eager to listen to you, ma'am. I talk only about seismicity, but today you will talk on probability assessment of earthquake occurrence in Northeast India. So we will learn from you. Thank you so much for accepting our invitation. Thank you so much. Over to Professor Zhao for his kind comments.
Okay, I'm very happy to attend this seminar by Professor Ghosh, and I'm quite interested in this topic, recent seismicity, and I want to learn from you. Thank you very much.
Thank you, sir. So now I'm going to do a short introduction of today's speaker to our participants. Professor Ghosh is presently serving as an associate professor and head Department of Civil Engineering, National Institute of Technology, Agartala. Her area of interest includes geotechnical engineering, soil dynamics, and earthquake engineering, analysis and design of footing, retaining wall, and slope under seismic loading condition, etc. Professor Ghosh pursued her BE and MTech from Indian Institute of Technology, Roorkee, and then completed her PhD from the same institute where she is serving presently. She has published more than 50 high impact paper in journals of national and international repute. So now, may I request Professor Ghosh to take this digital forum and enlighten us with her lecture. Over to you, ma'am.
So, thank you, sir. First of all, let me say that it's my immense pleasure for giving me the opportunity to say in that forum on second international virtual workshop on global seismology and tectonics, which is a prolonged program, 10 days program from 20 to 30 September 2021. And I'm going to speak on recent seismicity and probability assessment of earthquake occurrence in Northeast and Himalayan region. Mainly, I will concentrate on Northeast region. As we know, prediction of earthquake is till date, it's quite impossible. So we are just using some probabilistic model. We are just mentioning that, okay, within that period, this is the probability of occurrence of that magnitude earthquake like that way. For that, obviously, I have taken some research work. The works whose contribution is there, they are my MTech and PhD scholars, Sri Obik Pal, PhD scholar, Sri Shubham Gupta, MTech scholar, and Mohammad Sultan Hussain, again MTech scholar. So without their contribution, it is quite impossible. So thank you towards them also that they have contributed a lot to complete this work. So first of all, we all know that different types of faults, that means normal fault, reverse fault, and strike slip fault. Normal fault means that faults are moving in upward direction, but they are moving away from each other. Along the fault plane, they are moving away from each other, and reverse fault, same thing, but they are moving towards each other. And strike slip fault, whereas in case of normal fault and reverse fault, the fault is along the vertical plane, but in strike slip fault, the fault is in horizontal plane, and in movement is in horizontal direction. Now, if we go through the seismotectonic map of the study area, that means our northeastern zone and surrounding Tripura zone in between 1845 to 2009. So this is the scenario of this area. Now, if we concentrate on our state, that means Tripura state, and also northeastern part, it is seen that Chittagong earthquake occurred in the year 1762 of magnitude 7.5. Then in the year 1869, Kachar earthquake of magnitude 7.5. In the year 1885, Bengal earthquake of magnitude 7, 1897, Great Indian earthquake of 8.1 magnitude, and then Sri Mangal earthquake of 7.6 magnitude, and later on in the year 1930, Dhubri earthquake of 7.1 magnitude. So what can we say? That no large earthquake in last 89 years, and therefore this is the main point of concentration towards this region, that what may happen if any large earthquake comes during these recent days. Now, geological or tectonic settings, epicentral distribution and earthquakes, fault plane solution as given by Professor Coyle. This zone is divided into 6 zones. First one is Eastern Himalayan collision zone, then Indo-Burma subduction zone, and then Himalayan syntaxic zone, then plate boundary zone of Shillong Plateau, and then the intraplate plate boundary zone of Bengal Basin. So these are the 6 zones which are given by Professor Coyle. And then the studies on those areas using Gutenberg-Richter relationship, which is very well-known relationship. It is seen that the Bengal Basin, the B value is coming this mass, and for Shillong Plateau, B value is this mass, and like that way for other 4 zones, these are the B values. So what can we say? Lower the B value, there is a greater possibility to occur the large magnitude of earthquake. So here, what can we say, that out of this V value, this is the lowest V value, so there is a greater possibility to occur large magnitude of earthquake. So this is using the Gutenberg-Richter relationship. So these are just this relationship showing for all these 6 earthquake zones of northeastern regions. Now, coming towards this conditional probability. In a probability concept, the conditional probability is the probability that the future earthquake or event may occur during a given time interval after a certain elapsed time from the last event. The conditional probability, that means this is the conditional probability, which is the probability that an earthquake occurs during the next delta t interval, and is given by that equation. In terms of the probability density function, this can be replaced by that equation. Now there are four well-known probability distribution model. First one is I am going to mention here is oval distribution model. In this probability theory, the oval distribution is a continuous probability distribution. It is named, as we know, after Swedish mathematician Oval. The probability density function of a oval random variable is given by this equation. And putting this equation, probability, a conditional probability equation, and after integration, we will get this conditional probability distribution. So this is the oval distribution. Like that way, exponential distribution, same. This is the probability density function, and putting this value in the conditional probability equation, and after integration, we will get that equation. Same, Rayleigh distribution. This is the probability density function, and following same procedure. In the conditional probability equation, we will put that density function and we will go for integration to get the value of this probability using the Rayleigh distribution. Thereafter, Pareto distribution, same, it is the density function. We will put that density function in the conditional probability equation, and after integration, we will get this equation. Now, using this distribution, oval distribution and exponential distribution, four distributions are there. We are calculating the different parameters. What are the related parameters corresponding to this distribution? And then, on the basis of those parameters, we are calculating this time-dependent conditional probability of occurrence of major earthquake. Here, the magnitude we have considered 5.5 or more than that value. Now, here t equal to, we have taken that 0, 10, 20, 30 years. That means if initial time is 0 years, I am taking only one example. Sorry, then after 3 years from this 0 years time, what is the probability of occurrence of any earthquake of magnitude 5.5 or more than that magnitude? This is 40.59. Like that way, after 30 years, if initial time is say 30 years after the occurrence of any large earthquake, then after that 30 years, that means if we take delta t 3 years, that means at 33 years, what will be the probability of occurrence of any earthquake of magnitude 5.5 or more than that magnitude? This is 48.2%. So what I can say, this is for Bengal Basin, this is for Shillong Plateau, Indo-Burma region, and then Eastern Himalayan range. So here we are getting some probability 100%. I marked all these probability are red ink. So what can I say? That using this oval model, if we consider say initial time t equal to 10 years, then after 13 years, that means at 23 years, there is a 100% probability of occurrence of any earthquake of magnitude 5.5 or more than that magnitude. This is according to oval distribution. So these are the curves plotted using those oval distribution model and the calculation which we got the data considering this t equal to 0 to 30 years, and these are the probability. Similarly, if we use exponential model, the difference in this model and with other models is that for other models, we can consider the initial time, that means t, but here we cannot consider initial time. For any value of t, we have to calculate the probability of occurrence of any earthquake. So here only delta t we can consider, and here also we can see that for Indo-Burma region, some 100% probability of occurrence of earthquakes are there at 13 to 25 years. There is a 100% probability of occurrence of any earthquake. Now, these are just curves plotted using this exponential model. Now, using the Rayleigh distribution, say for all these basins, that is for all these earthquake zones, we are plotting this probability assessment for this is for Bengal Basin, this is for Shillong Plateau, Eastern Himalayan range, like that way. For all this zone, we are finding out the probability of occurrence of earthquake of magnitude 5.5 or more than that magnitude. This is the linear presentation of these earthquakes. Now, Pareto model. Similar fashion, using the Pareto model, we are getting these are the magnitude of their probability. Now, out of these four models, which one we'll consider that which will give us the best fit solution? For that AD test, we have conducted different tests on these probability models. This is one AD test, and according to these tests, the Rayleigh model is giving us 3.23, oval distribution 0.534, exponential distribution 0.37743, and Pareto distribution 2.815. So lower the value, that means this AD test, when we are getting the lower values, then we can say that this will give us the best solution. So here from oval solution and exponential solution, what is the probability we are getting? We can say that these are the best probability in comparison to this Rayleigh model and Pareto model. Similarly, for this is for Shillong Plateau, this is in the Mama region, Bengal Basin, Eastern Himalayan. For all these zones, we have calculated this AD value, and KS test also we have conducted. And accordingly, what we have seen that this oval distribution and exponential distribution, they are giving the best fit solution or best probability in comparison to other two models. Now, since this portion, we have calculated the probability of occurrence of any earthquake. What is the percentage of probability? Here, using this stochastic model, we are calculating the recurrence interval. That means this delta t time, that after what time that magnitude of earthquake will occur. So obviously, in that case, conditional probability value, it must be 1 or 100%. What should I say? That T delta T by T, it must be 100%, and therefore we have to maximize this conditional probability. And for this maximization, these are the two solutions we have to perform. Del P delta T by T by del delta T equal to 0, and next one is del P delta T by T by del T equal to 0. So in oval prediction, to find out this delta T value, we have used these two equations in oval distribution model, and we have calculated the value of delta T. Similarly, Pareto prediction, using the same two equations in the Pareto prediction model, we have calculated the value of delta T. Similar fashion, in Rayleigh prediction, we have calculated the value of delta T. Here also, we have calculated the value of delta T. Now, for all these zones, for Bengal Basin, say the initial time which we have considered, say 2017, in the year 2017, what is the observed value of earthquake we have seen? This is at 9.167. but predict, that means predicted using this exponential model, it is 6.16 years. So what is the difference? This difference is 3.007 years, and using Rayleigh model, same. This is the predicted value and this is the observed value. So difference is 3.337 years. Using Pareto model, this is the observed value, obviously it will be fixed, and it is the predicted, so difference is 3.025052, and here difference is 3.087. So if we compare all these difference, it is seen that their Pareto prediction is giving the lowest value of lowest difference. That means in earlier occasion, when we are calculating the conditional probability, then we are getting then you are getting that this oval distribution and exponential distribution, they are giving us the best fit solution or the best solution of probability. But here, when we are going for slides are not moving.
Yes, it seems so. Your slide is stuck.
Yes, sir, just a minute.
You take your time, no problem.
So similarly for Naga thrust, we have calculated this, that means date on which the earthquake occurred, what is the observed years, that means after which period this earthquake occurs, and what is the prediction using those models, and what is the difference. And here also we have seen that some difference in the observed values and predicted values, and in which case we are getting the less difference, that model we have considered the best model for that particular case. Similarly for Shillong Plateau, this Pareto prediction, that means Pareto model is giving us the lowest difference. Eastern Himalaya range also, this Pareto prediction is giving us the lowest difference. And similarly for Indo-Burma region, again this Pareto model is giving us the lowest difference. So what are the predicted values? If we consider that using the exponential model, then recurrence interval predicted is 1.25 years, And last event occurred on years is 7th January 2018, and next earthquake expected, that means adding this 1.25 years, next one expected is in the year 2019. So our study date, on which date we have conducted our study, it is 15 June 2018, and that means year left from the study date, it is 0.735 years. So next earthquake expected before 8 April 2019. Similarly, using Pareto model, if we consider the recurrence interval predicted is 1.0144, the last event occurred is 7 January 2018, and next earthquake expected is 2019, and study date obviously it is same. So year left from the present date, it is 0.4994. So expected date of next earthquake is 13 January 2019. Like that way, for all these zones, it is calculated. Now, what is the comparison we getting from observed values and predicted dates for last event in various regions in Northeast India? If we consider our probability distribution model, exponential model, the recurrence interval predicted is 10.198 years, but last event occurred on year 6 November 2013, and next earthquake expected to occur is 2024, and next earthquake expected before 13th February 2024. That means this one is converted in terms of date, and earthquake occurred, we are getting 24th April 2019. We are expecting that before 24th, we will be getting one earthquake, but we got it in the year 24th April 2019. So there is an error, 3.833 years using exponential model. Now, if we use this Pareto model, similarly, our recurrence interval predicted is 3.527 years. Last event occurs same. So next earthquake expected 2018, 25th November 2018. Earthquake occurred. Their date, so this is minus 0.33 years. Like that way, using Rayleigh model and using Gutenberg model, we can calculate. So out of all this, what we can see that this Pareto model, this is giving the least error, and what we can say in comparison to other three models, this is giving us very near solution. Okay, so like that way, for Eastern Himalaya region also we can calculate, and again we are getting that this Pareto model is giving very near solution in comparison to other two models. So what can we conclude? The seismicity parameter B value, as calculated using Gutenberg-Richter's relationship, shows that seismicity within the Northeast region is dominated by the Mississippi thrust and Bengal basin, which means they have higher chance of getting larger earthquake. The B value estimated for all these regions are, these are the B values for all these regions. The well-known probability models like exponential, Pareto, Rayleigh, and Gutenberg can be applied to the earthquake recurrence time interval to predict the next large earthquake in the northeastern region. For earthquake magnitude MW greater than 5.5, it is observed that out of all these models, the exponential model and Gutenberg model are appropriate distribution or more close to solution. What should I say? That appropriate, I cannot say exactly, more close to the solution for the northeastern region. Rayleigh model observed to be giving overestimation of recurrence time, whereas Pareto model gives very small recurrence time interval for the northeastern region. That means for recurrence time, this Pareto model is giving more close solution in comparison to other two models. Using conditional probability, recurrence interval has been predicted, and it is seen that the Pareto model gives us the small recurrence time interval, which varies from 0.438 years 0.4987 that means small variation we are getting in comparison to other models. So these are all, and these are the references we have followed to prepare this presentation. And thank you. Please visit NIT Agartala. And once again, thank you for very much for giving me the opportunity to say a few words. Thank you, sir.
Thank you, madam. Thank you for giving us such a deep understanding of probabilistic seismic hazard analysis. And now may I request our session chairman, Professor J. Kyle, sir, for his comment.
Yes, ma'am. You have really educated us in this morning. It was a wonderful lecture with wonderful analysis. And as you say, the probability of earthquakes in every tectonic zone, maybe mathematically there is some error of 2 years, 3 years, but there will be earthquake. So that is the, I think, concluding remarks I take home. So that means all the regions, all the tectonic blocks in Northeast India are vulnerable for strong to large earthquakes. And statistically, we have shown what is their probability. So I have just one comment that, yes, the whole region is probability is there for vulnerable earthquakes. So my appeal to you that you produce the engineers to make us a safe houses so that casualties is minimized, hazard is minimized. So as head of the department of the civil engineering department in NIT, you are really giving good graduates every year, and I interact with them. So we hope that in the language of Professor Jim Murray, that our engineers did good job. There were no casualties almost by the collapse of houses due to the mega earthquake in Japan in 2011. So I hope with your guidance, our future engineers will do the same job in our country. Thank you so much for a wonderful presentation, and you are always a good speaker. Thank you so much. Congratulations.
Thank you, sir. Thank you, sir.
Thank you, sir. So we have with us our session advisor, Professor Tapeng Zhao, sir, from Tohoku University, Japan. So I will request sir for his comments.
Okay, thank you very much for a nice talk, and it's quite interesting. I have just a question about the predictability of this approach. You showed two examples for prediction. One is for magnitude 5.6 earthquake, and another one is for magnitude 5.9 earthquakes, right?
Yeah, that 5.5 magnitude, we can take also 5.9 or 6. Generally, less magnitude of.
Can you do that for the magnitude 6 class or magnitude 7 class earthquakes?
Yeah, we can take, but generally it is seen that for that region, the magnitude of earthquake is less in comparison to other regions. The magnitude are less and depth are shallow. And this 5.5 magnitude is taken considering that recent earthquake in that particular region occurred in Tripura itself. It is very near 5.5 magnitude. That's why this magnitude is considered for that particular study.
Okay, so I have a question that for the same region, is the type of distribution the same for all magnitude earthquakes or different?
Then, sir?
For example, for the for the same region,
Yes, sir.
You know, for the magnitude 5 class earthquake, maybe it's a Weibo type distribution may works. For the magnitude 4, magnitude 3, cluster earthquakes, maybe another type of distribution works?
Yeah, yeah. This probability study will valid for all this magnitude. Generally, for a particular zone, we are considering that magnitude, which magnitude at that location may strike. This probability study, we can go for even magnitude 7, magnitude 8, magnitude 9, whatever magnitude we can consider.
Okay, so for the same region, you think that there's a typical type of distribution, right? For example, Poisson distribution or whatever. I'm sorry, I'm not quite familiar with the type of distributions. But for the same region, there's one type distribution working. Is that true?
Pardon, sir?
I just wonder if your type of prediction or the type of distribution,
Yes.
okay, for all magnitude events.
Yeah, all magnitude events it will be okay, but for this particular region, this 5.5 magnitude is vulnerable. That's why, as I'm telling, we have considered that magnitude. But for all magnitude, this prediction is valid. But as I am mentioning in the study of the starting of the presentation, we are just going for probability study using those models, and we have seen what is the percentage range of validation of all those models. When we are calculating the recurrence time, then Pareto model is more suitable in comparison to other models. But similar fashion, when we are going for the calculation of the probability, percentage probability, then in comparison to other models, our Weibull model is giving a better solution in comparison to Rayleigh model. Like that way, in comparison to Pareto model and Rayleigh model, this Weibull model is giving the best solution. So again, it depends upon the available earthquake data. If earthquake data or last earthquake data are less, in those cases, we are not get the very good probability study. We have to get good number of earthquake data. So
Okay,
for a particular region, if we go for probability study, then we can take any magnitude of earthquake. That will not be the issue.
Okay, then I suggest you to apply to the larger earthquakes.
Yeah.
Not only magnitude 5 clusters, because there's so many magnitude 5 cluster earthquakes everywhere.
Yeah.
So it's not so meaningful.
Yeah.
To make a prediction more meaningful and impactful, try to make it for larger earthquakes.
Yes.
That's what people are concerned about, right? And not only for this region, but for other actors like Japan.
Yeah. We have to do that.
Because, for example, in Japan, in China, there are longer history.
Yeah.
Of the historical earthquakes. Okay.
Yes.
So you can do this for the magnitude 7 or even 8 class earthquakes.
Yes.
Then it will be meaningful.
Yes.
It will convince most seismologists.
Yes.
Okay.
Yes.
Anyway, thank you very much. It's very interesting. Thank
you.
Thank you, sir.
Yes, Professor Jha, I fully agree with you. We should look for larger earthquakes.
Yeah.
Thank you so
this
much.
approach.
Very nice discussion.
Thank
you so much. Very nice discussion.
Not so meaningful. Try for big events. Magnitude 6, 7, even or 8 or 9. That'll be great.
Yes.
Thank you.
Thank you. Very nice discussion. Thank you.
Thank you, sir. Thank you. Once again to all of you for giving me the opportunity. Thank you, sir.
Some more questions will be there. Ma'am, some questions will be there. Please wait.
Sir.
Thank you, madam. Thank you, sir. Madam, now can you take some queries from the participants, if you permit?
Yes, sure. I will try.
Okay, madam. Then I request Dr. Antara Sharma to conduct the Q&A session. Over to Antara.
Thank you, sir. First of all, I would like to thank Professor Sima Ghosh, madam, for delivering such an informative talk. Ma'am, now I'm going to read out the questions asked by the participants. So the first question is, how you have computed parameters for probability distribution from earthquake catalog.
Yeah, for that we have gone through this determination of this. Just a minute. We have calculated the oval distribution. From the earthquake catalog, we have calculated this eta parameter and this theta parameter. Theta is the scale parameter and eta is the shape parameter. So this theta and eta are calculated using this earthquake catalog, and then using this equation, we have calculated the probability. And for that, maximum likelihood method is introduced. To get the value of theta and eta, the maximum likelihood method is introduced. And finally, we have calculated this probability, say, for oval distribution. This is the procedure. Again, if we go for this exponential distribution, so this E and mu we have calculated, and then putting this value of this probability density function in that equation, we have calculated the probability using this exponential distribution, like that way. So to calculate the value of this function, that means probability density function, this E, mu, and all these things for that particular probability distribution, we have used the earthquake catalog.
Thank you, ma'am. So the next question is how you have validated the recurrence time model for future prediction.
One second, please.
How you have validated the recurrence time model for future prediction.
Yeah, recurrence time model, if we go for recurrence time model, this stochastic model is used. So what we can say, for 100% probability, this conditional probability value will be 1. And for that, what we have done, we have optimized this one, that means maximized this one using these two equations. Again, all these four models we have used. All these four models we have used, and ultimately we have calculated the recurrence time interval. And we have seen from the tabular plotting of these values that which one will give us the minimum difference. That model we have considered that, okay, this is our best fit solution. Here this Pareto model is giving us the minimum difference.
Thank you, madam. Ma'am, the last question is, what are the different uncertainty you have considered in probabilistic prediction?
Different uncertainties. Obviously, there is one uncertainty is that the time which we have calculated this delta t, see there is a difference when we got the observed values. Just a minute. So there is a difference. So this difference means that this time lag which we have calculated is not exactly the exact solution towards the exact solution. So obviously that uncertainty is considered over there.
Okay, thank you, ma'am. Ma'am, due to time constraint, we cannot proceed for more questions. We will send you the questions through email. So thank you, ma'am.
Okay, thank you.
Thank you, madam. And thank you, Dr. Antara. So now we reach to the end of the session. So for this, I request Anvesha Datta Hazarika to propose the vote of thanks. Over to Anvesha.
Thank you, sir. Namaskar and good morning from India. It is a great privilege for me to propose a vote of thanks to all who have helped in making this technical session a resounding success. On behalf of the CSI NIST family and the entire organizing committee of IVWGST 2021, I convey our gratitude and sincere thanks to Dr. Sima Ghosh from NIT Agartala, India, for accepting our invitation and delivering such an interesting and educative lecture today on the topic Recent Seismicity and Probability Assessment of Earthquake Occurrence in Northeastern Himalayan region. Once again, thank you, ma'am, for enlightening us with your valuable insights and experiences. It was indeed quite helpful for all of us. I also express my sincere thanks and gratitude to Dr. G. Narahari Shastri, Honorable Director of CSIR NIST Jorhat, for extending his enormous support and guidance in conducting IVWGST 2021. I would like to extend my heartiest thanks to our international advisor of this workshop, Professor Andrew J. Michael from USGS, USA, for his valuable guidance and support. We are extremely thankful to our session advisor, Dr. Daping Zhao, eminent scientist from Tohoku University, Japan, for gracing this session today and for his unstinted support and constant encouragement. Thank you, sir. I would like to take this opportunity to extend our most sincere thanks to our session chairman, Professor J.R. Kayal, former Deputy Director General of GSI, and session co-chairman, Dr. Saurabh Borwa, Chief Scientist of CSI NIST, for their kind assistance in providing valuable suggestions and unflagging support in the organization of this workshop. My deep sense of appreciation and sincere thanks to all the attendees who chose to be live with us today and attended with great enthusiasm and cooperation and made it a successful event. Last but surely not the least, I thank the convener of this workshop, Dr. Shantanu Borwa, for his immense dedication and commitment towards this workshop and for giving us such a good platform to interact with the renowned personalities across the world. I also wish to express my deep sense of appreciation to the technical team and all the members of the organizing committee of IVWGST 2021 for their untiring efforts and hard work in successfully organizing this workshop. Finally, I solicit your continued support during the course of this workshop and look forward to see you all for the next session of the day at 7 p.m. Indian Standard Time. The speaker for the session will be Marco Pagani from GEM Foundation, Italy, and the topic of his lecture will be Introduction to the Open Quake Engine. With this, I conclude this session. Once again, thank you all for joining us this morning. Dhanyavad.
Thank you so much. Thank you all.
Thank you, sir.
Thank you, sir.